Hello, this is a video tutorial for the usage of the standalone version of Sesame. Sesame is a software package that we've recently released which solves a drift diffusion Poisson equation in 1 and 2 dimensions. So it's basically a semiconductor modeling software. And it's released as a Python library, so you can use that Python implementation in your own scripts, and is also released as a standalone executable that you can run in a Windows environment. And we'll talk about the standalone executable in this video. So you can see it takes a little while for the program to get started. That's because it has a complete distribution of Python in the executable. But here's a view of the main program window. It's divided into 3 tabs. So the System tab is where you define the system that you want to study. The Simulation tab is where you specify what kind of simulation you want to do, such as varying the applied voltage or varying the illumination. And finally, the Analysis tab is where you plot and analyze the results. And what I want to do in this video is to build a system from scratch and just kind of give you a sense of how it works. So what we want to do is build a 2-dimensional NP junction. Let's imagine that it's 3 microns by 3 microns. Here's a view of the system as we build it. And what we'll do is we'll build an N-type region on the left-hand side, P-type region on the right-hand side, and then add a grain boundary running through the junction. So the first thing we need to do is to define the numerical grid on which the solution is represented. So Sesame uses finite differences on a rectilinear grid, and what we can do is define a bunch of linear grids by specifying the first point, the second point, and the number of grid points between them. And we can concatenate these linear grids like this in order to have a non-uniform mesh. That's kind of important to have more mesh points where the solution is varying rapidly. So this is along the x direction. Let's do a similar thing along the y direction. So let me just choose some discretization here. This is slightly tedious and something we'd like to automate in future versions of the software. So that's going to be the grid. You see it covers from 0 to 3 microns in x and y. Next, we need to define the materials. So first of all, let's do the N-type material. First, we specify the location where the material is. And in this case, let's say that we have a material defined for x less than 0.5 e to the minus 4. Okay. Here we determine or specify all the material properties. ND is the donor density, and so let's say this is a somewhat heavily doped N-type semiconductor. So 1e17 donors per centimeter cubed, no acceptors. This is the effective density of states of conduction and valence band. Band gap, let's say 2.4. Dielectric constant 10. Effective mass of electron and hole. Here we have mobility of electrons and holes. Trap or defect energy level for bulk defect recombination. Note that this is measured with respect to the intrinsic energy level. So a value of 0 means that you have a defect at the intrinsic level. Here is the effective or the Shockley-Reed lifetime for electrons and holes. So I'm kind of picking numbers randomly here. Electron affinity in EV, radiative recombination constant, and Auger recombination constant for electrons and holes. Okay, so we've specified this N-type material, and we save it. And you see when we do that, we get a depiction of the system as it's been defined so far. So here is the x coordinate, there's the y coordinate, and you can see the type of grid that we've defined. Okay, let's add a p-type material. So we select new. In this case, the p-type is going to be all of the positions x above 0.5 e to the minus 4. And let's set the acceptor density to be 1e to the 15 per centimeter cubed. I'll change around some of these other numbers, make it a smaller band gap, 1.5, and choose new values for electron and hole mobility, and keep everything the same and go ahead and save that. And so here is the N part of the junction, here's the P part. Okay, next let's define a grain boundary that runs through the junction. So that's a planar defect. So we select new to define a new planar defect. And we define it by first specifying the endpoints of this planar defect. So let's say that the first position in xy is going to be, let's say, 0.2 e to the minus 4, 1.5 e to the minus 4. And the second point is going to be 2.9 e to the minus 4. Let's make it 1.7 e to the minus 4. Okay, so it's going to be running diagonally, something like this. Next, we define the properties of the defect associated with this grain boundary. So the energy level of the defect is specified here. That's again measured with respect to the intrinsic level. And let me select a value of 0.3 eV. Density of defects, this is per centimeter squared, so this is the number of defects per area on the planar defect or the grain boundary. Here are the capture cross-section for electrons and holes. And finally, the transition, the charge state of the grain boundary when the quasi-Fermi level is above or below the defect level. That is when the grain boundary defect is occupied or not. And let me choose -1 and 1. That sort of corresponds to having a donor and an acceptor at this same energy defect level. And we'll go ahead and save that. And you see here's a depiction of this defect running through the junction. Okay, in this box here we specify the illumination, let's say 1 sun illumination. This box specifies the absorption. You can either load that in from a file of the absorption coefficient versus photon energy, or you can just specify a fixed value for the absorption. Let's do that. Manual generation rate, that's a different sort of option which we won't discuss here, so I'll discuss that at some later time. But here we've basically done defining the system, so we can move on and specify the kind of simulation we want to do. So the two basic options are to cycle over voltages or to cycle over some variable associated with generation. And here I'm just going to talk about cycling over voltages, so we select that. Next, we specify the values of voltage that we want to cycle over. For this, we use a linspace function, which comes from the NumPy library. So minimum voltage value 0, maximum voltage value, let's say 0.8, and number of steps in between is 9. Next, we specify the output directory for all the data files that we'll generate. And remember, it's important to specify a directory for which you have write permissions. And so here I have a directory set up for that. Okay, output file name, that's the prefix for all of the output files which will be generated. So let's call it tutorial video. And the suffix associated with each of the output files will be labeled by the loop value index. Notice that the output file has two formats. One is gzip, so that's a compressed Python format. The other option is .mat, so that's a MATLAB file, which you can load with MATLAB to do analysis in that environment. Okay, next we have to specify boundary conditions. So I remind you that the way that the program is configured, we assume that on the left-hand side here is a contact, and on the right-hand side is a contact. For top and bottom, we can either use periodic boundary conditions so that the solution wraps around continuously from top to bottom, or we can use hardwall boundary conditions where the flux vanishes at top and bottom. So all of these are specified in this box here. Here we specify the type of contact we have at x equals 0, that is the left-hand side. The options are ohmic contact, Schottky contact, or what we call neutral contact. So here I've chosen ohmic. If you choose Schottky, then it's necessary to specify the metalwork function. For now, let's just use ohmic for the contact at x equals 0 and for the contact at x equals L. So that corresponds to the right-hand side of the system. For the transverse boundary conditions, that refers to the boundary at the top and bottom of the system. And again, you can choose periodic or hard wall. Let's choose periodic. Next, we have algorithm settings. So Sesame uses the Newton-Raphson method to solve these nonlinear equations. And this box gives you options for changing the algorithm settings. Typically, I don't mess with this too much except for the generation ramp, which I'll talk about momentarily. Okay, so we have everything set up. Let's go ahead and try to run the simulation. And so this box will give you an output of how the simulation is going. And you see actually the simulation in this case didn't go that well. So we first solved the equilibrium problem for the electrostatic potential in equilibrium. And after that's solved, we use that as a starting guess to consider the system driven out of equilibrium. And what we notice is that the algorithm diverged and so was not able to find a self-consistent solution. And so, okay, the reason for this is that when you add a grain boundary, typically you add a rather stringent nonlinearity to the system. And in order to achieve convergence, the trick is to increase this generation ramp. So what this is doing is it's decreasing the amount of illumination by 7 orders of magnitude. And it will gradually increase the amount of illumination in order of magnitude steps until you get to the one-sun illumination that you are interested in. So here's an example of what I mean. So we have the illumination divided by 10 to the 7. So now we're driving the system just very gently out of equilibrium. And so it's easier for the algorithm to find the self-consistent solution. And once it has that slightly out of equilibrium solution, it's easier to find the more out of equilibrium solution. And so you see that sort of smooths out the process of finding the solution. So it's going to run for a little while. While it does, we can continue to browse through these different tabs. So let me move on next to consider the analysis tab. So what we have here is a list of output files. We don't see any yet because we haven't completed any of the applied voltage values yet. As they're completed, this will begin to become populated. And once we have an output file, we have 2 options. We can either do a 2-dimensional plot in this surface plot box here, or we can do a 1-dimensional plot in this linear plot box. Now for the 2-dimensional plot, you can choose from this drop-down menu to specify the variable that you would like to plot versus position X and Y. And we'll see that in a second. So you see actually the first value of applied voltage just finished up. So we can go ahead and check that out now. If we plot the electrostatic potential, this is what we find. And so what we see here is the potential associated with an NP junction where we see an interruption of that sort of classic potential due to the presence of the grain boundary there. Okay, and we can look at other quantities as well. So if we take a look at, for example, the whole current, that will give us a map of the whole current in this junction at short circuit current conditions. So you can see that it's a rather complex pattern of whole current, and again that's due to the disruption of the standard NP junction by the presence of this grain boundary. So we can check in on the simulation and see how things are going. You see that now it's converging quite well. Let's go ahead and wait for it to finish up all the applied voltage values. Okay, so we're done. And let's move on to consider a linear plot. So in a linear plot, there's 2 options. You can either plot versus the a scalar value versus the loop values. So the typical example is just to plot the total steady state current versus the applied voltage. And Here we see the plot. So, okay, it looks like we didn't turn up the voltage enough to get to VOC, but you see that this is sort of the classic shifted diode curve associated with p-n junction under illumination. The other option for the linear plot is to make a plot of one of the solution variables in a 1D slice of the system space. So what you do in that case is you specify the endpoints of the 1D slice you want to look at. So let's select x equals 0, y is 2.5 e to the minus 4, so that's 2.5 microns. And for the other point, let's select x equals 3e minus 4, and also y, same value, 2.5 e to the minus 4. Let's go ahead and clear the plot we have already, and we can choose what we would like to plot along this 1D slice. Let's choose band diagram and make this plot. So again, this position is x equals 0, y is 2.5 e to the minus 4. That's first point. And the second point is x equals 3, y is 2.5 e to the minus 4. So we're plotting along this line here. So this is just the bulk part of the NP junction. And what you see is a band diagram, just like you would expect from a 1D NP junction under illumination. So we see splitting of the quasi-Fermi levels due to the illumination. And of course, these black curves correspond to the conduction and valence band edges. So what's interesting to do is to see how this to see how this band diagram, which we understand in terms of 1D NP junction theory, changes when you are traversing the grain boundary. So let's change the y coordinate from 2.5 microns to 1.5 micron, so that we're sort of in the vicinity of the grain boundary core like this. Let's go ahead and clear this plot and make a new plot. And you see a fairly distorted band diagram relative to the one just shown before. And so, that's the obvious impact of this charge defect, extended defect, which permeates through the grain boundary, or the NP junction. Okay, let's go ahead and clear this one out. One thing that's kind of nice for these position plots is that you can plot multiple files at the same time. So if I select all the files and then choose to plot the electrostatic potential, I get a family of curves corresponding to all of these different values of the applied voltage. Okay, so I think I'm going to wrap it up there. So there's sort of a whole slew of things you can study with this software, and this was just a tutorial to explain the basic operation of this GUI. And I guess the last thing I would say is that if you're interested in using this software for more heavy-duty research purposes to do large-scale parameter sweeps, I would encourage you to check out the Python library, because in that case you can sort of do cluster calculations where you can run as many simulations simultaneously as nodes you have access to. Okay, thank you very much.